Hello students, I welcome you all to the e-learning sessions of LJ Institute of Engineering and Technology. Myself Hardik Shah, and today we will discuss about Willians line method to finding the power. Okay, so I hope you will see this video till the end to completely understand the topic and to gain your automobile skills. Fine, so let's start our video. Willians line method is used to find the frictional power of the engine. Okay, in Willians line method we will plot the graph of specific fuel consumption over the torque. So here we can say that we will extrapolate the graph, which is partially a straight line, to zero specific fuel consumption, and note down the torque, which gives us approximate value of frictional power. The figure you can see here, okay, it will give you more clarity about the Willian line method. But this test is only conducted in a CI engine. Okay, so what is that and why it is applicable only to CI, or you can say diesel engine, not in petrol engine? Because for that you need to understand the governing system. Fine. So what is governing, or you can say what is qualitative governing? So in petrol engine we can keep air fuel at constant rate, okay, and vary the amount of mixture intake for required torque or power. Okay, this is called quantitative governing. Okay, so in diesel engine we draw a constant volume of air, or you can say compressed air, and vary the fuel injection. Okay, so technically we alter the quality of the air fuel mixture. This is called qualitative governing. Okay, we cannot apply Willians line method in SI engine. Why? Because at lower speed in SI engine, in lower speed the air mixture intake is very low. That is quantitative governing. Okay, hence there will be a low pressure region created inside the cylinder, due to which there will be pumping losses. Okay, therefore there will be more frictional power than the real, or you can say actual one. Okay, so we get bad output, you can say uneven output, if we use the Willian line method for the SI engine. So if we use the same test for CI engine, there is qualitative governing, not quantity governing. Okay, and hence there will be a fixed amount of air entering the cylinder and no negative pressure and no pumping losses occurs. Okay, so we get relatively closer value to the actual value of the frictional power. Okay, so the errors are minimized in this CI engine. Okay, so that's why we are using the indicated power, that is we are using the Willians line method in diesel engine. Okay, so this is your diesel engine test setup for performance of the Willians line method. Okay, and this is your engine, which is the single cylinder 4-stroke diesel engine, which is connected with the electrical dynamometer. This dynamometer is connected with a coupling. Okay, and here one tachometer is provided to measure the engine speed in terms of RPM. Now this is your U joint, which is coupled with a electronic dynamometer. Thereafter the load balance is given for measuring the load condition, and with this engine you can see here the test rig is connected. Now what is this test rig? It is actually mounting of the different components like fuel tank, burette, thereafter U-tube manometer for the measurement of the different components. Here you can see RPM meter, that is the RPM meter, and the temperature indicator is also given, and you can also see here one air box, which is actually useful for the supplying of the air in a diesel engine. Okay, so this is the air box, and here you can see a big pipe, which is actually called hose pipe, which is connected with the engine. Okay, so this is your air inlet connection with the air box, which is supplying the air inside the diesel engine. Okay, this is the fuel line, which is connected with your burette. Okay, you can see here this is your fuel line, which is coming out from the burette. Okay, and this is the fuel tank from which we are actually supplying the real fuel to the engine. Okay, so for test fuel we are using the burette, and for another thing we are using the engine. So here it is the fuel on off valve. So when it is off, the fuel is coming from the burette, and when it is on, the fuel is now coming from the fuel tank. Okay, so this was the main connections inside the engine. This one is the gas calorimeter. We can say it is useful for the exhaust gas temperature measurement, and you can see here these are the temperature sensors, right? So these are the temperature sensors which are useful for the all the different types of working, and we are rotating the water inside it, so it will cool it also. Thereafter the load bank is also given here. This is the load bank, in which you can simply see different types of loading is given. So the total of the 4 kilowatt capacity is having here. Okay, so when you actually
on the means thereafter when you apply the different load in a iterative manners, you can simply see that there are the different notations written here. So if I on the 100 and 500, the total kilowatt will be 1.5 kilowatt. Okay, so this way we will actually give the load to the engine. Now here also you can see this is the water flow. Okay, and you can also see here this is the water meter. Okay, which is actually showing us the flow of the water. Okay, in our experiment we will keep it constant, almost 7 or you can say 7.5 liter per R capacity. Okay, so this is the notation that how this flow meter works. Okay, so what we will do, we will actually take the reading in a for a 10 ml of the fuel, and thereafter we will actually start our calculation mode. Okay, so this is the whole engine, you can simply see. So this was our experimental setup for the understanding the Willians line method. Okay, so now we will start taking the calculation on this engine. Okay, and this is the temperature sensor for the gases. Also you can put it in an exhaust gas chamber. So this is the PT100 sensor, which is actually useful for the checking inside the test rig. Okay, so in this manner we can check all the temperatures inside the engine and the test rig. So in this manner we can simply see that this is the basic setup for the diesel engine, and we can perform heat balance sheet method and the experimental setup over the Willians line method. Fine. Now here you can just mark the initial diesel level. Okay, because we are actually measuring the 10 ml of the diesel for the measurement. Okay, so whenever the diesel stops inside the burette, just make one mark from which we can say that it is our starting point, and after the 10 ml make a second mark which will be our ending point. Okay, so what we will do, we will just mark 2 points, one with the initial level and second one is a final level. Okay, so this is how we will actually do our experiment. So now let's do the experiment and take the readings. Okay, so here we are starting the engine. So engine is started and we will let it stable. So we will achieve the stable RPM, and once the stable RPMs are achieved, we will start our experiment. Okay, so let it become steady first, and you can see here also some load is actually applied over the engine, and it can be shown in a this spring balance. Okay, now here this is the load bank. Okay, so this is right now actually in off condition. You can see there is no loading condition for the engine. Okay, the total capacity is 4 kilowatt, and we will apply the load on the engine. Okay, first we are actually checking that water flow is coming or not, or it is perfect or not. Okay, and thereafter what we will do, we will start the experimental setup. Okay, in which you can simply see here the RPM is now showing in a tachometer, and you can also see the different types of temperatures. Fine. Now what are these temperatures that I will show you during the calculation? So first we have already marked the diesel level, okay, in a burette, and this is the main setup in which we are connected to the load bank. So first what we will do, we will check that either load is on or off. Thereafter we will start our load bank. First we will apply the 1 kilowatt, that means we are applying it in a successive manner. So after applying, we will let it stable again. So we will see this on a spring balance that now engine is stable condition. Okay, so we have totally applied, you can see here 50 plus 100 plus 100 plus 250 plus 250, that is 100 watt, that 1000 watt, that is 1 kilowatt. Okay, and the same is reflected on a spring balance. Now we will actually note down the RPM. Now first RPM was 1550 and it is reduced to 1509, and you can also see there is a rise in temperature. Okay, and this is the air pressure in which the manometer is shown, and this is the burette which we are using for the measurement of the fuel consumption. So after opening the valve, we will start our stopwatch and we will keep it on until our next, we can say, 10 ml is consumed. Okay, so for 10 ml we will measure the time. Okay, and for that we will need a stopwatch. So here you can also see the stopwatch is working, and the levels is actually coming down. That means the diesel is consumed in an engine. So here you can see it is a 10 ml end. Okay, this is the final level. So up to which we will take the stopwatch. Okay, and once this level is achieved, what we will do, we will actually just stop it. So we can just see here the stopwatch is ended at the 38. Okay, so in 38 seconds we have measured that 10 ml of the fuel is going inside the engine at exactly 1 kilowatt. Okay, so this is how we can take all the measurements. Okay, so now what we will do, we will actually apply the similar all the loads like 2 watt, kilowatt, 3 kilowatt, 4 kilowatt, and we will measure all the timings for the consumption. Fine, and once we get all the consumption timings, we will do our final calculation in a different manner by the formulas that what are the main factors which are actually applying during the engine condition, and once done we will stop the engine. We have achieved all the readings for the heat balance sheet method as well as Willian lines method. So next we will see how the performance calculations are done. So let's start the calculation. So here is the data for our 4-stroke single cylinder diesel engine. So basically this is the basic data that we will take during our calculation. So first you can see here, this is the density of the water, thereafter density of air and the fuel is given, thereafter the bore diameter and the stroke length for the given engine is also given. Okay, the brake drum diameter, that is the 300 into 10 raised to minus 3 meter, it is also given for the calculation purpose, and thereafter these are the other calculation which is required only in a rope diameter, which is actually required. Fine, so this is the basic data that we will use for the calculation of our experiment. So now let's first see our observation table. So here what we will observe, so as I told you that you will be given different types of load. Okay, so we are actually giving the load in a 4 manner. First we will go no loading condition, thereafter we will increase the load one by one, so it will be 1 kilowatt, 2 kilowatt, 3 kilowatt and 4 kilowatt. Okay, so this is your observation table for all the loading conditions. Thereafter we will actually measure the RPM from the RPM meter, which is indicator. Okay, and we will write the RPM over here. Thereafter we will use the time which is required for the 10 ml fuel consumption that we are actually measuring by the stopwatch, that we will write in a third column. Thereafter we will measure the manometer difference, flow rate. Okay, it is almost constant in all the loading condition because we are only watching regarding the fuel consumption. Okay, and thereafter we will also measure different types of temperatures, but basically the temperature which is we are using is cooling water temperature. Okay, so this is the basic observation table, and thereafter we will do the calculation of the performance factor. So this is the calculation for the performance factor. First we will find the brake power, thereafter we will find the fuel consumption. Brake power is actually you are applying, that is the 1 kilowatt up to 4 kilowatt. Okay, thereafter fuel consumption, it is having the different formula, so it is x by t 10 raised to minus 6 into density. Okay, and here x and t is what, the x is the amount of oil consumption, in our case it is 10 ml, and t will be timing in a stopwatch. Okay, so that after finding this fuel consumption we can find easily specific fuel consumption depending on our loading condition. So the formula will be SFC equal to FC upon BP. Okay, so thereafter we can also find different types of heat, but that we will find during the heat balance sheet. Okay, so for Willians method we only need two things, one is IP and second is brake power. Okay, and we are also finding the fuel consumption. Thereafter what we will do, we will use this graph to draw our Willians line method. So what we will do, we will actually plot the brake power and the fuel consumption points. So here you can see we are actually drawing a one graph on which on x direction we are taking the brake power, and on y direction, or you can say y axis, we are taking the fuel consumption. And after plotting all the points regarding fuel consumption and the brake power, what we will do, we will actually take that line on a reverse. So we will extend that line on a reverse side, in which we will find the cutting point of the horizontal line. Okay, that is horizontal x-axis, and on that direction we will find that is our frictional power. Okay, so from this graph you can simply see that it is called Willians line method. Okay, so now let's see all these things one by one by taking the sample calculation. So here you can see this is the sample calculation that we have just taken. So for 1 kilowatt the consumption time is 42 seconds and the RPM is 1500 RPM. Okay, so now if we increase the loading condition, the RPM will decrease and the fuel consumption will increase, so it will take less time to get consumed. Okay, so for 10 ml fuel we are getting all these times, and in this case we are keeping the manometer difference which will remain almost constant because we have the constant speed engine, and the flow rate is also constant because it is a water flow rate. Okay, and we will observe the temperature. Almost in most cases the temperature one remain constant, that is 29 degree, that is almost approximate nearby room temperature. Okay, and the T2 will actually increase as we increase our loading condition. Fine. So here you can see it is actually we are getting, that is 33, 34 and 36 degrees. Okay, so this is the basic table that we will use for our sample calculation. So for calculation purpose, what we will do, we will find the brake power, we will find fuel consumption, and thereafter we will plot our graph. Okay, so now let's see first how to find the fuel consumption. So here it is the sample calculation given. Okay, here you can simply see the brake power is taken 1 kilowatt as we are only applying 1 kilowatt. Now after fuel consumption is taken, so fuel consumption equal to x by t into 10 raised to minus 6 into density of the diesel because we are using the diesel engine. Okay, so density of the diesel, that means rho f, density of fuel, into 3600 as we are finding it in a kilogram per hour. Okay, so keeping it all the conditions, that x is actually 10 ml, we are using the 10 ml fuel, t which is taking time, that is 42 seconds for the 10 ml for 1 kilowatt. Okay, and the rest things we will put as per our given data. So we will find the fuel consumption, that is 0.72 kg per hour. Okay, now we have found the brake power and the fuel consumption. So what we will do, we will draw one graph on which we will mark this point. That means on brake power we will mark for 1 kilowatt, and in fuel consumption we will mark 0.72. So by connecting both of the lines we will get 1 point. Okay, now same thing can be done for the second observation, that means brake power is 2 kilowatt. So here it is also given, that is the observation number 2, that is brake power is 2 kilowatt, and the same formula we are getting the fuel consumption, that is 0.945. Okay, so from these two values we can simply again plot the same values in the graph, and we will get more 1 point on a graph. Okay, thereafter let's take observation number 3. So brake power is 3 kilowatt, and the same way we will get the fuel consumption, that is from the formula, that is 1.26. Here you can see we are actually spending 24 seconds for the 10 ml fuel consumption, so we will get 1.26 kg per hour. Okay, we will plot the same points on a graph. Okay, now let's take fourth observation, that is 4 kilowatt. So in this manner we will get fuel consumption, that is 1.778 kg per hour. Okay, and we will plot all these things. So here you can see simply in one table, that is observation 1, brake power is 1 kilowatt, FC is 0.72, and in the same manner you can simply see 4 observations. Okay, so this is the main table that we can say we are actually using it for finding our Willians line method. Okay, so we will take brake power on a x-axis and we will take fuel consumption on our y-axis. So after plotting all the points we will get this line, and when we extend this line we can see here that the graph is actually extended on a behind y-axis. Okay, and if we measure that point by a scale or by a different manner, we will get that FP is almost 0.9. Okay, so we are getting the FP, that is frictional loss, and this is the main idea, main aim of our practical. So now we are getting the FP. Now once the FP is achieved, that is frictional power is achieved, we can easily find the indicated power also, that is brake power plus FP. So it will be 4 plus 0.9, that will be 4.9 kilowatt. So this is the idea about the experiment, and this is how we are actually getting the friction power. So now let's see about the applications of this Willians line experiment.
So we have studied two methods today. I am repeating both of them one by one. The first one was Morse test and second one was Willians line method find. In Morse test we are finding the IP of each cylinder by cutting off each cylinder one by one. Now what is the meaning of cut off? Cut off means we are actually switching off the single cylinder and we will continue all the cylinders at the same speed. Okay, and this is actually done by connecting the dynamometer and we will find the IP. Okay, so we are cutting off all the cylinders one by one and thereafter we can get the power of each cylinder and we can find that what is the problem in any cylinder. So if you can say that there is one car, that is Maruti 800 car, and it is actually 4-cylinder car. Let's assume that it is 4-cylinder car. Okay, so we can say that in each cylinder there will be 200 cc. Okay, so we can get power of 200 cc in each cylinders. Now if there is any problem inside the engine, so we need to find in which cylinder the problem occurs. Okay, so for that we can conduct this type of test and we can find the real problem of the in which cylinder it is happen. Okay, so we need to check only IP of each cylinder. In any cylinder, if IP is less than the 200 cc achieved, so we can say that there is a problem inside that cylinder. Okay, so for that we are using MOS test. And what is Willians line method? We are only taking the readings of the torque and the specific fuel consumption. Okay, and we are only plotting one graph, and by this graph we can say that when we extrapolate, or you can say when we extend this graph to the negative side, we will get one point on a torque side. Okay, and that is our frictional power for that engine. Okay, so that's it in today's session. In next session we will discuss more about the MOS test and heat balance sheet. Fine. So I hope you have liked this video and you like this video. So please you can also subscribe this channel to get more videos like this. Okay, so keep learning and thank you.